Okay. So, who's got it? And I solid. Who's got this? Who's doing it? Tristan. All right, go ahead. And I solid plus.
Ni plus 2AQ.
Ni plus 2 AQ. So let me just recap. This is losing electrons. It's going through the wire into this solution. Nickel plus 2 is gaining that, producing
Ni plus 2AQ.
Ni plus 2 AQ. Ni solid, right. I mean, this is kind of silly, but that's exactly what happens. We could throw the old equilibrium in there just because it could go the other way, possibly. So this is our anode, this is our cathode. So why is it important to write this? Now you know who the reactants are and who the products are. It might seem silly because they're literally the same species, but the concentration is different, right? So which one is the 0.1 and which one is the 1? So when this loses electrons, so this is definitely a reactant because this starts off the whole show. Who is it reacting with? Which Ni plus 2? This one or this one? First or second? Try again. These nickel ions are gaining electrons. This is this Ni plus 2 right here. These ions are a product of this metal losing electrons. So this is my 0.1 molar. This Ni plus 2 is my 1 molar in the first scenario. This is the hardest part of a concentration cell with the same elements. It's confusing. I'm not going to pretend it isn't. If it was different elements, and I'm going to do a problem with different elements, but I started with the harder one. If it's the same element, you really got to think about what's going on in the cell. So obviously I can teach you and show you and give you some tricks, try to, but when you're given a problem like this, you really need to analyze and think about what's happening. The electrons are coming from this, so that's a reactant. They're going over here. If nickel plus 2 in this solution wasn't here, the reaction wouldn't happen. So those are my two reactants. Even though they're separated, that's kind of irrelevant. They're not really separated. The whole cell's connected. It's a circuit. So this is losing an electron, 2 of them, and they're going here. Why is this really important to understand? Now you can calculate Q. So my Q is going to be 0.1 over 1. So let's actually calculate this. Now, in this scenario here, right, so we have E equals E cell minus 0.0257 over 2 times the natural log of 0.1 over 1. Right? Is that the right number? I think it is. 0.02. Yeah? Okay. So, what is the E cell? So I want you to write this down. We're going to use it just to teach the concept. Again, they're not going to ask you to calculate the voltage, but they might ask you this scenario. They might ask which scenario creates a higher voltage and why. So that's what I'm trying to teach you. Not the calculation, I think, just helps me explain. So, what's this? How would we figure E cell out for the exact same element? Go to page 823. What is the reduction potential for Ni plus 2 to Ni? Negative what?
0.25.
So, negative 0.25? Okay. So, if one half reaction, nickel is losing, and then the other half reaction, it's gaining, right? So this one's gaining electrons. Think of it this way. So this is plus 2 electrons. This is gaining, turning into that. What's the E cell? So if my oxidation, right, it's anode, or it's cathode minus anode. E cell equals cathode minus anode. If my cathode is negative 0.25, and my anode is negative 0.25. It's the same exact number. What's the E cell?
0.
Is it always 0? For these examples?
Yeah.
Yes, if it's the same metal, that's always 0. That should make sense to you. If it takes this, think of it this way. If it takes the same amount of voltage to lose an electron as it gains, right, the signs are just flipped, it's going to be 0. That should make sense. So this is 0 for both of these, right? So we're going to calculate the E for this and then the E for this. So this is 0. Someone do this number for me here. 0.0257 divided by 2. 0.01285. And now this is multiplied by the natural log of 0.1 over 1. So we'll do 0.1 divided by 1. Take the natural log of it. Go ahead, Nicole.
The natural log would
Do
be
the whole thing, yeah.
negative 2.3025.
Just give me one more second. Or two more. Negative 2.3, give me two more numbers. 0, 3. Okay. So now our E is going to be 0 minus that number times that number, which makes it a positive number. We agree on that? All right, and what do we get?
0.0296.
0.0296. All right, so that's my E for this one. Everybody calculate the E for this one. So it's just, the only difference is natural log of 0.01 divided by 1, right? So you guys should be able to just bang this out real quick. So 0.01 divided by 1, take the natural log of that. I guess Nicole, what is that number? Just the natural log of 0.01 divided by 1.
Negative 4.605.
Negative 4.605. Okay. So, what is our E, Nicole? 0.0592. Volts, sorry, I forgot my unit. All right, voltage goes up. So after all of that, I hope most of that made sense to you, or some of it, I'll take some of it. This was the point. The end goal here was understanding, well, really two things. In a concentration cell, if your oxidation half cell is less concentrated than your reduction, it will be spontaneous, thermodynamically favorable. If it's not, if it's flipped, if it's the same concentration, or if it's flipped, then it's going to be non-spontaneous. We want the oxidation to have less concentration because we need space, like empty desks, for those ions to jump into. That should make sense. Doesn't make sense, and I'm going to have, who's it going to be? Luke. Doesn't make sense, this number is bigger than this number, and if it does, tell me why.
It does make sense, because we're going to make more ions for the oxidation cell.
Right, so basically, yeah, good. This should be bigger, and I'm just going to use the desk analogy. This is more empty desks. So let's say I have an unlimited number of students in the hallway. Let's say every desk in this room is empty. More of them can come in. So the smaller this concentration, right, essentially the bigger the difference between these two numbers, the bigger the voltage. The further, think of it this way, from equilibrium. Because once these two reach the same concentration, the cell stops. That's equilibrium. That's where the AP test is going to try and get you. They're going to give you a concentration cell. They're going to ask, they may not even give a whole lot of numbers. They may say, explain what happens to a concentration cell if the concentration of your oxidation half cell and reduction half cell are equal. You would say it's at equilibrium, it wouldn't produce any voltage. They could also ask, all right, what if there's a large difference in the concentration? Then you would say there would be a higher voltage produced because it's further from equilibrium. So it's hard for me to replicate all the questions, obviously, just on the fly here. But this is the whole concept. The further apart these concentrations are, the higher the voltage. Again, more empty desks mean more ions, more students can come sit down. That's a good thing. That runs the cell and creates electricity. The closer these numbers are together, the closer to equilibrium, and the closer to zero that will be. So hopefully that makes sense. Right, because what's the natural log of 1? 0. What's 0 times anything? 0, right? So if this is 1 divided by 1, this is 0 times 0, the whole thing is 0. Right, so when those concentrations are equal, this is 0. So that would be equilibrium. So let's kind of write that, summarize what we just learned, and then we're going to move on. Alright, so in a concentration cell, this is kind of the last thing here, in a concentration cell, the I'm going to say it a couple different ways here. The larger the Q, the larger E, and that's using this equation. So again, I teach the equation because it just helps me explain it. I don't know. I just think it's easier when you have concrete things to look at instead of just trying to learn concepts. So if Q is bigger, then E is going to be bigger. That's what that statement means. So if that makes sense to you, and the math makes sense to you, and you can remember this equation, that'll help. It's not on your reaction sheet. Alright, but that's one way to explain it. The other way, I'm not going to repeat in a concentration cell, but the larger the difference in the concentrations of the two half cells, the larger the E, or voltage. And we gave those examples. So if it's 0.1 and 1 or 0.01 and 1, the bigger the difference, the more voltage it's going to produce. And one more thing I want to add to that, I know there's kind of a lot with this. I'm trying to be clear, I'm trying to take my time with it, so hopefully you're picking up most of this. But I know it's hard. The other thing that they're going to ask, or they might focus on, is what this really means is it's farther from equilibrium. Once E is 0, the cell stops. Because the reverse and the forward isn't favored anymore. So the further away that those concentrations are from each other, that's why I like talking about the equation. The further away from 1 Q becomes, the better. That's the further it is, that's the longer it'll run, that's the more juice you'll get out of it, more voltage. That's what that means. So if this makes sense, great. If this makes sense, great. I'm saying the same thing. Hopefully something here makes sense to you. Let's hope this year they give us just like a regular galvanic cell. So we just learned E cell, delta G, and K. I think maybe right now those seem easier than this. Right? This is a little complex. It's the same method. All right. I was gonna give you one of the. I'm gonna give you. I'm gonna have you use this on a homework problem, maybe at least one, maybe two, and it's gonna be with 2 different metals. So if you go to page, just to show you what I'm talking about, but I'm going to give it for homework because I'm going to do electrolysis because that's it. It's like the last thing. If you go to page 830, if you're not there already, look at the very bottom, example 18.6. So it gives you cobalt and then it gives you iron plus 2. The cobalt's giving iron plus 2 electrons, and there's your cell. Underneath it, it tells you the CO plus 2 is 0.15 and the Fe plus 2 is 0.68. So it gives you the concentrations, right? So you're not standard. So if it's not standard, meaning 1, then now you're using this Nernst equation, and it wants you to, I don't know, what is it asking? Predict if it's spontaneous or not. So you would have to look up the reduction potential, so go to page 831. you would look up the reduction potentials, find E cell, that's negative 0.16. From that number, we already know it's not spontaneous. It's not thermodynamically favorable. And that's because the way the reaction's written is backwards. Iron is more reactive than cobalt, so that the way they wrote it doesn't work spontaneously. But then you solve for E using the concentrations they give you. Products over reactants, the way they wrote it, cobalt plus 2 is a product, Fe plus 2 is reactant. You take everything, plug it in that equation, you solve for E, you get negative 0.14, which is not what we want. That's not spontaneous, right? So that's what I'm going to give you. I'm going to give you something like that for Monday. All right, just so, again, I think it's good. Using the equation helps you understand how E changes based on concentration. So you will do at least one or two of those. I really hope they don't give you one of these like the backwards cells, you know, because they might give you this reaction and have you explain the spontaneity of it or the thermodynamically if it's favorable or not. I just think that's kind of a cheap shot, but let's practice anyway, right? So I want to practice just in case. All right, so we are done with galvanic cells and concentration cells. I think we're good there. All right, electrolysis now. Cal, you awake?
Sure.
All right. So Cal, when I say electrolysis, what do you think of? Anything? Anything come to mind? Electricity, that's good. That's a good start. What about Taylor? When I say electrolysis, what do you think?
Like water.
Water. Good. What's going on? That's an electrolytic cell, and there's almost always water involved. I know it's kind of a small picture here. So we're going to write in our notes electrolysis. I want you to draw something that looks like that, except we're not going to use this example. Wait a second. Okay, yeah, we can use this example. So this is molten salt in here, liquid salt. So in this thing here, we have NaCl liquid. So the goal here, in about 20 minutes, kind of explain how to do electrolytic calculations, and then we'll have to continue with this tomorrow. So draw that in your notes. This is called an electrolytic cell. What's the big difference, Paige, between a galvanic cell and an electrolytic cell? You want me to zoom in a little bit? There's a battery. Good. This is non-spontaneous. Electrolytic cell electrolysis is not something that happens on its own. We have to force it by giving it electricity. The battery is a voltaic cell. That is a galvanic cell. That's spontaneous. That's thermodynamically favorable. This is not. This is how electroplating works. You guys remember when I copper plate things in the back? Everyone usually remembers that. That's using electricity to perform a chemical reaction. So galvanic cell, it's using chemical reactions to produce electricity. This is the opposite. It's using electricity to perform a chemical reaction. So we're going to need page 823 for this, for sure. So make sure you got that handy. Yeah, they don't really give a very good, yeah. So there's not a great picture in the book here, but let's say this is the electrolytic cell. We have two pieces of metal, anode, cathode. The signs here are flipped. So the anode in electrolytic is positive and the cathode is negative. Again, the curriculum, the new curriculum tells me kids won't have to label that. All right, well, I'm going over it anyway, but whatever. If you don't remember that, it's not the end of the world. The electrons still go from anode to cathode. It's still fat cat, gains mass, anode loses mass. This is still oxidation over here. This is still reduction. Everything we've learned still applies to this. It's just calculating the voltage, or calculating the voltage, and the calculations are a little different. So that's what we're going to get into. All right. So I want you to actually write these down too. So if you have salt in this container and you run electricity through it, your anode is where oxidation occurs. So whatever's in the solution, whatever's in this beaker, whatever's in this container, the ions, the substances in here are going to get oxidized over here. Whatever's in here that gets reduced is going to happen over here. In this case, when you have molten salt, NaCl liquid, you only have two things in there. You have Na plus, Cl minus. So I start with an easy example. You only have two ions in here. There's no water, there's nothing else. So you have Cl minus being oxidized, and you have Na plus being reduced. So these half reactions, I'll write them over here to make it a little bigger. 2Cl minus yields Cl2 plus 2 electrons. So that's my oxidation. My reduction half reaction is 2Na plus 2 electrons yields 2Na solid. And the ions are aqueous. Cl2 is a gas. Oh, I'm sorry, liquid, because it's really hot. Sorry. Liquid, sodium. So, what's going on in electrolytic cells? Most questions involve calculating E cells from a given reaction or a picture. So the hardest part, and we're going to get into a harder one, the hardest part is figuring out what's being oxidized, what's being reduced. Then you go to the chart and look up the reduction potentials and do cathode minus anode. So that's kind of, I just summarized everything in one sentence there. This is an easy one. When it's just one substance, not a solution. When it's a solution, you have water involved, it gets tricky. When it's just one substance, you only have one option for each of these. So let me ask you guys this question. Does it make sense to anybody sitting here that Cl minus is the one that's losing electrons and Na plus is gaining? Trevor's shaking his head, yeah. If you look at these half reactions, why does that make sense? Go ahead, Trevor.
Because Cl minus has an extra electron.
Yes, good. Cl minus has the electrons to lose. Na plus doesn't. It already lost one, right? So remember, this is non-spontaneous. These cells only work because you're forcing it with a battery. Cl minus doesn't want to lose an electron. Cl minus has 8 valence electrons, so does Na plus. But when you hook it up to a battery, it actually forces it to. So Cl minus turns into Cl2 gas because it loses those two, and then Na plus gains those and becomes Na liquid, which is also pretty stable. Those are stable as well. So you would actually see bubbles at this thing over here. That would be chlorine gas. I've seen AP questions. They give a picture like this. They don't label the ions. They tell the student what's in here, and then they draw bubbles around one of them. And one question is, what are the bubbles made of? That's kind of hard, right? It might seem easy now because it's kind of going backwards. But if they don't tell you what's going on here, you have to figure it out, right? You have to figure out what's in there and what could the bubbles be. It's almost always chlorine, hydrogen, or oxygen. One of those three. It's almost always one of those three. But don't put that in your brain and memorize it, and then you get to the AP test and it's like nitrogen or something. You still have to figure it out. All right. So let me use this simple example to teach how we're going to do all the ones moving forward. Go to page 823. I want you to calculate the E cell for this electrolytic cell. How do we do that? Well, go to 823. Let's look up both of these. And I want to write the voltage down next to it, all right, or above it, or whatever, wherever you have room. So find this one, this Cl minus, and then find the Na plus. Find the voltage on there. And then I want you to do cathode minus anode. Let's see what you guys, we should all get the same number. And remember, because there's two NAs, that does nothing to that number. Whatever those numbers are, always just leave them the way they are. It doesn't matter that there's two NAs because there's also two electrons. So think of it like they kind of cancel out. It doesn't matter. So these volts are the same. So go ahead and calculate the E cell. Again, it's cathode minus anode. And soon as somebody has it, just yell it out. Somebody probably already has it. You leave me, hang me out to dry here. Who's got it?
Negative 4.07.
Negative 4.07 volts, he says. Anybody else get that one?
Yeah.
Yep.
Let's double check. What's this one? What's the E cell for this? Or not the E cell, it's technically just the E. What's the voltage of this here? 1.36 volts, and what's the sodium here? 2.71 volts, right? Okay, so it would be the cathode, right? Here's my cathode, here's my anode. It would be negative 2.71 minus 1.36, right? Which gives us negative 4.07. Okay, yeah. That's a strange number. That's a pretty big negative number. Okay? What's the problem? From what we've learned so far. Not problem, but what does that mean? Let me rephrase that. What does the negative E tell us? It is not favorable. Right? So negative delta G is thermodynamically favorable. Positive E is thermodynamically favorable. Should this be positive? No. What did I tell you about these cells? They're not spontaneous. They're not favorable. How do you know that? Right. Good. So I'm hoping there's, I'm saying a lot today. We're learning a lot. Hope there's certain things that are sticking, making sense to you. All right. Look at your chart again. Which half cell is the lowest out of those two? Or which half reaction? Na, right? Na is pretty close to the bottom, and Cl is pretty close to the top. Right? So this is going to be the one that's reduced. This is the one that's going to be oxidized because it's the exact opposite of what we learned with the galvanic cell. If you look at the bottom, those are all really reactive metals. Naturally, they want to lose electrons. So they want to be oxidized. But this is the exact opposite of what they want, right? This is not spontaneous. It's not favorable. So the way I teach this is if you're given two half reactions, and by the way, we're going to do one where you're going to have four. I'm going to give you two options for this side, two options for this side. You have to figure out which one actually works. That's the hard part. That's what last thing we're going to do. But when it's only two options, it's a lot easier. So the way I teach it is, and some kids don't like how I word it, so it's up to you. But the more positive voltage is going to be your oxidation, and then the more negative voltage is going to be your reduction. That's just how I remember it, so that's how I teach it. That's how I write it down. I don't think I have another way that I worded that. Hold on. Yeah, the more positive reduction potential is my cathode, and the more negative is my anode. Wait, what did I just say? Is that what I said the first time? Is that what I said the first time? See, now I'm in my own head. Did I say that backwards the first time? Anyways, we're gonna do another example. So that's what I'm trying to get you to understand is if you look at your chart, they're pretty far apart. You just have to understand if they give you four half reactions on an AP test, because they don't give you. I really wish they would give you this chart, but they don't. So instead, they'll give you these with their values. You have to figure out which one's which. So I use this as a starter because it's easy. It's just 1 and 1. I'm going to do one with you now where there's going to be water involved. So we're going to do the exact same thing. We're going to calculate E cell, but we're going to do it in water. So we're going to do KBr AQ. So in this solution, we're going to have K plus is Br minus, but we also have water. So let's do that, and we'll end with that. So that example will help you understand a little bit better, because when it's only actually two examples here, one and one, it's almost harder to see what I'm trying to teach. So it's trying to make it easier, but it might be more confusing. So let's do this again. All right, so draw draw a cell. All right, this time we have KBr, AQ. You have a piece of metal here, piece of metal here. All right, battery here. All right, here's my anode, here's my cathode. All right, so this is where oxidation is occurring. This is where reduction is occurring. All right, so the question is, if you have a solution of potassium bromide, calculate the E cell, right? So a solution of KBr in an electrolytic cell, calculate your E cell, and they would give you, let's see, where are my notes here? I'll actually use my notes for this one. They would give you 4 reduction potential. So I'm going to write all 4 down. Just give me a second here. All right, so I'll put them over here. So we have K plus 1 electron yields K. So I want to make sure I write it the correct way. Hold on. Where's that? Where's that? Where the heck? So, go to page 823. I'm losing my mind right now. Find the reduction potential reaction where there's water on one side and 4H plus on the other. I can't find it. Yeah, where is it? There it is. There it is. There it is. Got it. Thanks. Okay. See, that's the thing. I was going to write it the wrong way. I'm trying to make this like as hard as I can. I wrote it in my notes like the way that makes sense. I'm going to give you what the AP test will give you, which will be the one that doesn't make sense. So basically I'm just going to write it the way I have. Okay. Here we go. So write these down. So this would be given. They give you a picture, maybe not actually. But the question is, you have a solution of KBr, calculate the E cell given the following. All right, they give you this, then they give you this one here. That's going to have to be 2, right? 2 Br. Then they would give you this one, O2 plus 4H plus 2 electrons yields 2 H2O, and then the other one down there, 2 H2O plus 2 electrons yields H2 plus 2 OH minus. Yeah, okay, so there they go. I should probably fix that in my notes. Alright, so okay, so technically these are liquids. Gas, this is aqueous, liquid, aqueous, this is gas, liquid. I think that might be liquid or it must be solid actually. And then AQ. What does it say? Yeah, solid. Okay. Alright, so now they would give you all 4 of these like in a chart with this question, and they would give you the voltage. I don't have room over there, so I'll write it over here. So the E for this one is negative 2.93 volts. The E for this one is positive 1.07 volts. This one is 1.23. 1.23 volts positive, and then this one is negative 0.83 volts. Okay. All right. So obviously we're running low on time. So this is a typical AP problem as far as an electrolytic cell. They give you a solution, and again, they have to give you these. Maybe this is actually easier instead of giving you the whole chart. So they're telling you, okay, you got to use something here. Well, this is where we're gaining electrons. This is where we're losing. You have two half reactions that could possibly happen here, and two half reactions that could possibly happen here. Only one of these is the half reaction going on here, and only one of these is going on here. So you have four options, one here, one here. So you have to figure out which one is which. So if we're looking at this here, let's think about this. What are the only three things in this solution? This is how I like to think of it.
Water.
H2O, K plus.
BR minus.
Right, so this is how I teach it. Hopefully it'll make sense to you guys. Is it fair to say, we understand, you have a beaker of water and you dump some KBr in it, it dissociates, so this is what we have. Okay, now the way I want you to look at these is find these substances. This one for species. This one, and this one. Okay. Here, K plus is gaining an electron. Here, so I know it's all written the same direction, right? So that's why some of these are like backwards. And that's what Liz was saying earlier. That doesn't mean we change the number. But here, if we think of it the other way, Br is losing 2 electrons. So here, K plus is gaining. Here, Br is losing 2. Here, water is losing 2. Here, water is gaining 2. So, Leo, Gert, right? So this would be an example of oxidation. This would be an example of reduction. This is an example of reduction. And this, nope, I said that backwards. This is oxidation. And this is reduction. So let me just explain what I just did there. On an AP test, if they give you a solution, they're going to give you 4 options. 2 options are going to be with the ions, 2 options are going to be with the water. You have to figure out, is it the water that's getting reduced over here, or is it the Br minus that's getting reduced? Is it the K plus being oxidized, or the water? So that's what we have to figure out. So I'm going to just repeat myself. How do I know which one's which? I look at what's in the beaker and what's happening in the half cells. Here it's gaining. I said that backwards, didn't I? Sorry, guys. That's reduction. This is, I said it exactly backwards, I'm sorry. It's hard to get it all straight even for me, especially after 2 periods of going on and on. Sorry. So K plus is gaining, Leo Ger, gain electrons reduced. So that's how I know this is a reduction half reaction, because that's gaining. How do I know this is oxidation? Because it's losing, Leo. The water is losing, that's oxidizing. The water is gaining, that's reducing. That's really important, or you never do these problems. You have to identify who's oxidized, who's reduced. Now you've narrowed it down. So I know over here, it's going to be one of these 2. And over there, it's going to be one of those 2. How do we know? The way we figure it out is which one would rather, or which one is stronger? Which one is going to get reduced and overpower the other one? Is it going to be K plus or H2O? Is it going to be Br minus, or is it going to be H2O? Which one's going to lose electrons? So now we look at the reduction potential sheet. I still use the whole sheet as an example here, and that kind of helps us figure it out. Okay? So I know we're basically out of time. So let's just do the oxidation first. So Br minus losing 2, or water losing 2. Well, what would make sense? We think Br minus losing 2. Okay. Now over here, reduction, gaining, who do you think would want to gain electrons more? The K or the water?
Okay.
So some of us said K. The value and the sign on here is how we figure it out. Okay? The value and the sign is how we figure it out. Let me read it, and then we'll just end here. We'll pick up with this tomorrow. The more positive is the cathode. The more negative is the anode. So out of those numbers, that's how we figure it out. You're probably tapped out. You probably have been for 10 minutes. So we will pick up exactly where we left off tomorrow. I'll put all this back up there and we'll pick up with it. So don't forget the thermo quiz. And that's it.